All right, buckle up, everybody, because today we're taking a deep dive into something pretty complex,
Oh, yeah.
but super relevant, especially if you're, working on a chemistry or materials science grad program.
Definitely.
Nanocatalysis for CO2 reduction to methanol.
It's a hot topic.
I know, I know, I know you've all got a solid foundation in chemistry out there.
For sure.
But what we're really exploring today is like the cutting edge. How do we use nanotech to take a greenhouse gas and actually turn it into something useful?
Yeah, like a fuel,
Yeah, or even a chemical building block.
a building block.
Yeah. So it's pretty cool.
It's a pretty amazing shift, actually.
Yep.
We're moving away from like this whole idea of CO2 being a problem and environmental liability,
Right.
and starting to think of it as a resource.
Yeah.
Like imagine a future where we're not just, capturing carbon,
Yeah.
but we're actually using it to create the stuff, the materials that we need.
That's awesome. Okay, so paint a picture for me. Why is methanol so valuable?
Well, okay, so we're trying to move away from fossil fuels, right?
Yeah, yeah.
So methanol is amazing because it's so versatile. I mean, it's already being used in all kinds of industries.
Okay.
Like think plastics, resins, fuel cells.
Wow.
And, as we're all moving towards hopefully a more sustainable future, its potential as a clean energy carrier, I mean, that becomes even more important.
Yeah.
We can just use it directly as fuel
Oh, cool.
or even convert it into other useful chemicals, even other fuels.
Wow, that's really versatile. But
Well-
how do we make that happen?
Yeah.
CO2 to methanol, that's not like a simple reaction.
No, not at all.
It's not just one step.
It's a bit more intricate than that.
Okay.
At the heart of it, you've got CO2 reacting with hydrogen gas, and that produces the methanol and water.
Okay.
So the basic equation, it looks like this. CO2 plus 3H2, and that gives you CH3OH plus H2O.
Okay.
And it's exothermic,
Which means?
which means it releases energy, but like a lot of reactions, it needs a little push to get going. Oh, so it's like needing a spark to light a fire, even though burning releases energy.
Exactly.
Yeah.
And that's where the catalysts come in. They lower that initial energy barrier.
They make it easier to get started.
Exactly, yeah. Catalysts basically provide like an alternate reaction pathway,
Okay,
and it has lower activation energy.
got it.
So the reaction happens more easily.
They're like facilitating the molecular interaction.
Exactly, like they're matchmakers,
I like that.
bringing the molecules together just right
Yeah.
so the transformation can happen.
And I'm guessing not all catalysts are created equal here.
No, definitely not.
Right.
Especially when we're talking about something as specific as CO2 reduction to methanol.
Right.
We need catalysts that are efficient, of course.
Sure.
We want them to promote the reaction that we want,
Right.
but they also have to be very selective.
Okay, what does that mean in this context?
So selectivity means we want to make as much methanol as possible.
Maximize that yield. Exactly. But at the same time, minimize any unwanted byproducts.
Oh, so there are other reactions happening.
Oh, yeah. And this is where it gets tricky.
Okay.
Because there are other reactions that want those same reactants.
Oh, so there's like a competition for the CO2 and the hydrogen?
Yeah, you could think of it that way.
Okay, so what are we up against? What are these other reactions?
Well, the two main culprits are the reverse water-gas shift reaction.
Catchy.
We often call it RWGS.
Okay.
And then there's methanation.
Methanation, okay.
And these reactions, they can basically steal away our CO2 and hydrogen.
Oh, no.
And then instead of getting methanol, you end up with carbon monoxide and methane.
Not what we want.
Not exactly.
So it's not just about getting the reaction to happen, it's about getting the right reaction.
Exactly.
So that's where the nanocatalysts come in, right?
Yes. Nanocatalysts, they're like the superheroes of this story.
Okay, I'm intrigued. Tell me more.
Okay, well, they have several advantages over traditional catalysts.
Yeah.
First of all, they're incredibly small.
How small are we talking?
Typically less than 10 nanometers.
Wow.
And that means they have a much larger surface area compared to their volume.
Okay.
And that translates to more active sites where the reaction can take place.
Gotcha. So faster reaction rates.
Exactly.
It's like having a whole army of tiny catalysts working in parallel.
That's a great way to put it.
But that's just one piece of the puzzle.
Yeah, there's more.
What else makes these nanocatalysts so special?
So because they're so tiny, we can actually fine-tune their properties.
Okay.
And we can do that in ways that just aren't possible with bulk materials.
Interesting.
We can really carefully engineer the composition, the shape,
Yeah.
even the structure of these nanocatalysts.
To do what?
To optimize their activity, their selectivity, their stability.
For this specific reaction.
Yeah.
Wow, so we're talking about manipulating matter at the nanoscale to get, like, tailor-made properties.
Ex-
That's amazing. But, before we get too deep into the specifics of all the different types of nanocatalysts,
Yeah.
maybe give us a quick crash course on methanol itself. Like, where did this even come from?
Right. Good point. So methanol, it's got a long history, actually.
Really?
Yeah, I mean, it goes all the way back to ancient Egypt.
Right.
They used to get it from wood pyrolysis.
Interesting.
And then in the 1920s, that's when large-scale production really started.
Okay.
And they used a process called syngas, which is a mixture of carbon monoxide and hydrogen, and it was derived from fossil fuels.
Oh, so like natural gas or coal.
Exactly.
Wow.
Yeah. And actually, that process is still widely used today.
Oh, wow.
But, it relies on non-renewable resources.
Yeah.
And, of course, generates quite a bit of CO2 emissions.
Right. So kind of counterproductive to what we're trying to do.
Yeah, exactly.
So even though methanol has this huge potential as a fuel and a building block, the way we've been producing it isn't really helping with that sustainable future we're all hoping for.
Right. That's why this idea of using CO2 as the feedstock is so appealing.
Yeah.
We're essentially closing the loop,
Yep.
Taking something that was a waste product and turning it into something useful.
Yeah. It's
Yeah.
like we're not just reducing emissions.
Yeah.
We're actually using the CO2 to create valuable stuff.
Exactly.
I love that.
And the cool thing is, by using nanocatalysis,
Yeah.
we can potentially make this process not just environmentally friendly,
Okay.
but economically viable, too.
So it's a win-win.
It's a win-win.
I'm ready to learn more about how these nanocatalysts actually make this happen,
Great.
but we'll have to save that for the next part.
Sounds good.
We'll be back after a short break to explore all the different types of nanocatalysts being developed.
We'll dive right into the specifics.
And we'll look at the challenges and opportunities in this exciting field.
Absolutely.
So stay tuned.
We'll be right back. So, ready to dive back into the nanocatalysts? Oh, yeah. We've talked about methanol, how awesome it is, and all the reaction challenges.
Right.
I'm ready to hear how these nanocatalysts actually come into play.
Okay, so one of the most, I guess you could say, studied catalysts for
Yeah.
this whole reaction
Yeah.
is copper.
Copper.
Copper, yeah.
Oh, okay.
It's relatively inexpensive.
It's good.
And it's shown, good activity for CO2 reduction to methanol, especially when we get down to the nanoscale.
Okay. But why copper? What about it makes it so effective for this reaction?
Well, copper has this unique electronic structure
Like,
that lets it bind CO2 and kind of activate it for the reaction.
gotcha. So it's like helping it get ready to react.
Yeah, and by manipulating copper at the nanoscale, we can really enhance its catalytic properties.
What ways?
So for example, we can create copper nanoparticles with specific facets
Okay.
or shapes,
Uh-huh.
and that can dramatically improve their activity and selectivity.
Oh, wow. So it's not just using copper, it's using it in a very specific way. Exactly. It's almost like we're sculpting the catalyst at an atomic level.
To make it work better.
Exactly. Yeah. It's about creating those active sites on the copper surface that are just right for the reaction.
And that makes it favor making the methanol.
Yes, exactly. Over all those other side reactions that we were talking about.
So cool. It's like we're molecular architects here.
Right.
But copper isn't the only thing, right? People are looking at other materials too.
Oh, yeah, for sure. There's a whole world beyond copper.
Okay, like what?
Well, researchers are looking into noble metals,
Noble metals.
like
Okay.
palladium and platinum.
Okay, I've heard of those.
And they're known for, they have really high selectivity for methanol.
Okay.
But the problem is they're really expensive.
Ah, so it's a trade-off.
Yeah. Performance versus cost.
Are there any other materials that kind of hit that sweet spot between the two?
Yeah, researchers are looking at some promising alternatives,
Okay.
like indium
Indium.
and gallium.
Gallium. Okay.
And these metals have shown some interesting activity and selectivity for CO2 reduction
To methanol.
to methanol,
Okay.
and they're potentially more cost-effective.
Okay. So it sounds like we've got a lot of options here.
Yeah.
A whole periodic table of possibilities.
Yeah, periodic table is our friend.
But, okay, let's talk about those side reactions again. The RWGS,
Right.
the methanation, the ones that kind of want to steal away our methanol.
Yeah, they're always lurking.
How do these nanocatalysts suppress that?
Okay, so one approach is to actually control the size and shape of those nanoparticles.
Okay.
So smaller nanoparticles, they often have a higher proportion of under-coordinated surface atoms.
Undercoordinated. What does that mean?
It means they have more kind of free electrons, you could say.
Gotcha.
And that makes them more active and selective for the methanol pathway.
Oh, so it's not just about having more surface area.
No.
It's about having the right kind of surface
Yeah,
area.
exactly. You got it.
That kind of likes methanol.
Exactly. That wants to make methanol. Another strategy is to modify the surface
Modify the surface.
of the nanocatalysts
Right.
with what we call promoters or ligands.
Promoters or ligands?
Yeah, think of them like tiny little molecular assistants.
Okay.
They can kind of help steer the reaction in the right direction.
Okay, so they like help the catalyst do its job better.
Exactly. They can like enhance the binding of CO2 and hydrogen, or they can hinder the absorption of like unwanted byproducts.
So they're like blocking the bad stuff.
Yeah, exactly. Keeping the reaction path clear for methanol.
I like it's like giving those molecular matchmakers from earlier
Yeah.
a little bit of extra help.
Yeah, a little nudge in the right direction.
Yeah.
Now, you mentioned something before about supports for the nanoparticles.
Oh, yeah.
What do you think the role of those supports is?
I'm guessing it's not just like holding them up.
You're right.
It's got to be more than that.
It's super important. Think of it like a foundation for the nanoparticles. Provides stability.
Okay.
Prevents them from clumping together.
Oh, right, because if they clump together, they're not as effective.
Exactly.
Okay, so what kinds of things are used as supports?
Well, we often use metal oxides,
Metal oxides.
things like zinc oxide, alumina,
Yeah.
ceria,
Okay.
and these oxides can interact with the nanoparticles
Okay.
in a lot of ways.
Yeah.
They can influence the electronic properties
Okay.
and even change the catalytic behavior.
So it's not just a passive support.
No,
It's actually kind of part of the reaction.
exactly.
They're working together.
They're a team,
The support and the nanoparticles.
the dynamic duo.
That's awesome.
Yeah.
So are researchers looking at other things for supports?
Oh, yeah, always. They're always exploring.
Like what?
Things like carbon nanotubes,
Oh, wow.
graphene.
Okay.
They have those unique properties,
Yeah.
that can like really enhance catalyst performance.
So we're really engineering these materials at like such a tiny scale to get the best catalyst possible.
Absolutely. Optimizing every little detail.
That's so cool.
Yeah.
But you mentioned something before, even more advanced structures,
Yeah.
like core shell nanoparticles.
Core shell.
What's the advantage of that?
So imagine a tiny capsule,
Okay.
and in the core, you've got the metal,
Okay.
and then it's surrounded by a shell,
A shell of a different material.
a different material, right?
Okay.
And that shell can act as a protector.
Oh, like preventing the metal from deactivating?
Exactly.
Or like sintering.
Yeah, keeping it pristine.
So it's like a suit of armor,
Yeah, a little nanosuit.
protecting it from the harsh reaction conditions.
Exactly. Keeps them in fighting shape. You also asked about single atom catalysts.
Yeah, those are crazy.
Right.
How does that even work?
It's the ultimate inefficiency. Imagine each individual metal atom
Okay.
just dispersed on the support. So we're maximizing the use of that metal. Every single atom is working.
That's incredible. It's like taking those tiny matchmakers
Yeah.
and making them even tinier.
Yeah, atomic level matchmakers.
But okay, we've talked about the CO2, we've talked about all these amazing catalysts,
Right.
but there's one thing missing,
What's that?
the hydrogen.
Yes, the hydrogen. You're right.
Where did we get that from?
That's a crucial part of all this.
Yeah.
Because if we're aiming for sustainability,
Yeah.
we can't be using hydrogen from fossil fuels.
Right. It defeats the purpose.
Exactly.
So green hydrogen
Green hydrogen.
from like water electrolysis
Yes.
using solar or wind power.
Absolutely. If we want to make this whole process truly sustainable,
Yeah.
we've got to integrate CO2 reduction with green hydrogen production.
To close that carbon loop.
Exactly. Close the loop. Make it all truly green.
This is where it gets really cool, I think, for a lot of us.
Yeah.
It's not just chemistry anymore.
It's like chemistry, material science, and renewable energy all coming together.
Yeah, you need all of them.
It's like this perfect storm of different fields.
It's a multidisciplinary
So
challenge.
it's huge.
Yeah, we need a holistic approach.
So efficient, stable nanocatalysts,
Yes.
new reactor systems,
Uh-huh.
and then green hydrogen production.
All working together.
It's a lot. But the payoff
Oh, it's huge.
to be able to capture those CO2 emissions
Yeah.
and use them to make valuable chemicals and fuels.
And power it all with renewable energy.
It's amazing.
That's the vision. That's what we're working towards. And with all the advancements that are happening
Yeah.
in nanotechnology and renewable energy, I think we can make it a reality.
Wow, we've covered so much ground in this deep dive.
Yeah.
You know, from that basic chemistry of CO2 reduction
Yeah.
to the super intricate world of nanocatalysts.
It's amazing, isn't it?
It's clear this field has so much potential for tackling climate change.
Creating a more sustainable future,
Absolutely.
especially for all of us working in chemistry and material science.
Yeah, it's a really dynamic area of research. And it's exciting to see all this progress that's being made.
It is. It really is. But as with any emerging technology,
Yeah.
there's always those challenges, right?
Right.
Before we can see it really being used everywhere.
Yeah, for sure.
So what do you think, what are the biggest hurdles we still have to overcome to make this commercially viable?
Well, one of the main challenges is stability.
Stability.
Yeah, catalyst stability. I mean, we
Right.
need catalysts that can operate efficiently for a long time
Okay.
and not lose their oomph, their activity.
Right. Because those reaction conditions can be pretty harsh, right?
Yeah, exactly. Elevated temperatures, pressures, all that.
It takes a toll.
It can lead to deactivation over time.
So it's not just about finding a catalyst that works great in the lab.
No, not at all.
It's got to be able to handle those real world conditions.
Yeah, in an industrial setting, you need something robust.
And that's where the material science really comes in.
Absolutely.
We need to develop new materials or even modify existing ones
Yeah.
to make catalysts that can just really stand up to those tough conditions.
Yeah, and that might involve trying different support materials,
Okay.
alloying metals, even developing protective coatings.
Oh, for the nanoparticles.
Exactly.
That's so cool. It's this whole new frontier for material scientists to explore.
It really is.
What about reactor design?
Yes.
Are there specific engineering challenges there?
Oh, definitely. I mean, designing those efficient and scalable reactors
Right.
for CO2 reduction to methanol, that's another big hurdle.
Because they have to be able to handle those high temperatures and pressures.
Exactly. And ensure that, the reactants are really in good contact with the catalyst.
Yeah.
So optimal contact.
And it all has to be cost effective and energy efficient, right?
Oh, absolutely.
So it's not just pure chemistry anymore.
No.
It's bringing in all these different fields: chemical engineering, material science, process design.
It's like a team effort,
It really is.
bringing together all these different expertises.
And of course, we can't forget about the green hydrogen.
Right.
That integration is key.
Absolutely crucial. I mean, the whole sustainability of the process hinges on that.
Right. Because if we're using hydrogen from fossil fuels, it's what's the point?
Yeah, exactly. We're just shifting the emissions problem.
Yeah. We need to make sure that entire chain, from hydrogen production to methanol synthesis, is clean.
Powered by renewable energy.
Exactly. It's all interconnected. And for all of you out there, those of you listening who are in grad school,
Yeah.
there are so many opportunities in this field.
It's ripe with opportunity.
It's amazing. It's almost like we've laid out this roadmap for future research.
Yeah, a path forward.
We need those better catalysts. We need more efficient reactors.
Yeah.
And we need that integration with renewable energy sources.
Seamless integration.
Yeah.
It's a beautiful thing.
It is. And there are so many questions left to answer. I mean, how can we make these catalysts even more selective? So we're really maximizing that methanol production.
And minimizing the byproducts.
Exactly. And can we design totally new reactors that can work at lower temperatures, lower pressures,
Yeah.
to save energy?
That would be amazing.
It would. And how can we optimize that interface between the catalyst and the support
Yeah.
to make it even more stable, even better performance?
So many questions.
So many exciting questions.
And I have a feeling a lot of the answers are going to come from all of you.
Yeah.
The grad students out there.
The future scientists.
Yeah, who are really pushing those boundaries in chemistry, materials science, engineering.
It's all in your hands.
It is. It's an exciting time to be in this field.
It really is.
So to all our listeners, keep exploring.
Keep asking those tough questions.
Don't be afraid to challenge things.
Yeah. And keep pushing those limits.
The future of sustainable chemistry, it's right there.
It is. And it's in your hands.
Absolutely. And remember, scientific discovery, it's a collaborative thing.
Yeah.
Share your ideas, work together.
It's all about teamwork.
It really is.
Well, that's fantastic.
Yeah.
I think that's a perfect note to end on.
I agree.
So until next time, keep those scientific minds buzzing.
Stay curious.
Stay curious.